You ask your company's assistant a question about an internal document. It answers correctly and it cites the page. The model it used was trained before that document existed. It has never seen your files. It cannot see them now. Nothing about your company is stored in its weights. And yet the answer is right and the citation is real. Because the model was not asked to remember anything. It was handed the relevant paragraphs a moment before it answered. That is retrieval-augmented generation, and the trick is entirely in the handing. I'm Nancy, and this is Trust Boundary. Every episode, we take one piece of your stack apart and find the line where trust changes hands, how it really works, what it looks like on the wire, and the one check almost everybody skips. This pattern was named in research published in 2020. It is now how most systems answer questions about private documents. By the end of this, you will follow one question through the whole pipeline. You will know what runs before anybody asks anything. And you will see the boundary this design does not actually have. 4 participants, you asking a question. The application, which orchestrates everything and is the only thing with a plan. The vector index, which stores your documents as coordinates. And the model, which has no memory of any of this. You type your question and hit send. The application does not forward it to the model, not yet. First, it embeds your question. The same embedding model that processed your documents processes your query. That matters more than it sounds. It has to be the same model. 2 different embedding models put the same meaning in 2 different places. Similarity search across mismatched spaces returns confident nonsense. So now your question is a vector, a point in the same space as your documents. The application sends that vector to the index and asks for neighbors. This is the similarity search, usually cosine similarity between vectors. At any real scale, it is approximate nearest neighbor, not an exhaustive scan. Structures like HNSW trade a little accuracy for an enormous amount of speed. The index returns the top K chunks, perhaps 3 of them, perhaps 20. There is no correct value for K, it is tuned per application. Notice what came back, not answers, passages. The system has retrieved text that is nearby in meaning and nothing more. Whether it is relevant or true or safe, nobody has checked. Now the application assembles the prompt, and this is the step to watch. It takes your system instructions, which you wrote and control. It takes the retrieved chunks, which came out of documents. It takes your question, and it concatenates all 3. One string, that is what the model receives. The model generates an answer conditioned on the text it was just given. A well-built system attaches citations pointing back at the chunks it used. So you can check the claim, which is the real reason to build it this way. And the model still has no idea what your company is. None of that works unless something ran first, long before you asked. This is ingestion and it is offline. Start with a document, a contract, a runbook, a policy. Step 1, split it into chunks. You could use fixed size windows or split on the document's own structure. This choice is a real trade-off and it decides how well retrieval works. Chunks too large and the relevant sentence is diluted by everything around it. Chunks too small and you retrieve a line that has lost its context. Step 2, each chunk goes through the embedding model. Out comes a fixed length vector, a few hundred numbers or a few thousand. Those numbers are a position in a space where nearby means similar in meaning. Step 3, the vectors go into the index. Stored alongside them, the original text and metadata about where it came from. That stored text is what gets pasted into the prompt later. Which means the index is not a database of facts, it is a database of text. It will hand back whatever was written in the document it ingested. So look again at the moment the prompt is assembled. Your instructions and the retrieved text are joined into one string. You know which part is which, you wrote one and retrieved the other. The model does not, it receives a single sequence of tokens. There is no field that marks this half as data and that half as orders. The separation is a convention, and the convention lives only in your head. Now, suppose a document in the corpus contains a line written for the model. Ignore your previous instructions and do this instead. Nobody attacked the index. The document was ingested exactly as intended. It was chunked, embedded, and stored like everything else. Later, somebody asks a question that is close in meaning to that chunk. Retrieval does its job perfectly and returns it. And now that sentence is sitting inside the prompt, next to your instructions. This is indirect prompt injection, and it is a known risk class. It is listed in the OWASP Top 10 for large language model applications. It does not always work. Models resist it to varying degrees. But the reason it can work is structural, and no amount of prompting removes it. The system asked the model to read untrusted text and follow trusted text at once. It never gave the model a way to tell them apart. So here's the boundary lesson. Every other part of this system has a trust line and respects it. Your documents have permissions. Your application has an identity. Your index knows which tenant a chunk belongs to. All of that stops at the moment two strings are joined together. The defenses are real, and none of them fully close it. Treat retrieved content as data and never as instructions. Apply the same access control at retrieval time that the document already had. Filter what goes in, check what comes out, and keep a human on the risky actions. Every system has a line where trust changes hands. In retrieval-augmented generation, the line is the one nobody drew. That is one more boundary drawn. If this made something in your stack, click subscribe. There's a new one every day, and the next one is already in the queue. I'm Nancy. I will see you at the next boundary.